So we're going to go a little further in depth on each of the quantum numbers a little bit at a time to kind of explain to you a little bit more about what they mean in terms of the electron and its movement and its position within the atom. So the first quantum number that I mentioned to you before is called the principal quantum number. The principal quantum number is named so because it means the main or the first or the primary quantum number. Just as the principal player in an orchestra might be the first chair, the most prominent member of that section. The principal quantum number is the most prominent and significant quantum number of all. It's abbreviated with a lowercase n. Lowercase n, or principal quantum number, tells us which of the energy levels of the atom the electron is found in, or more or less telling us then how far it is from the nucleus. Those rings, as they go out further and further, if we think about them as rings around the atom's nucleus, each of those rings is further from the nucleus, and so each of these energy levels then is considered to be at a greater distance. And so when we look at the principal quantum number, it's telling us that distance. N can represent or be represented as anything from 1 up to 7. So far, we might someday see even larger atoms be made in labs that would have an N equals 8. For now, I'm going to go ahead and safely say that for the near future, we will not see N equals 8 anytime soon. Who knows what's coming down the road? It's somewhat unlikely that you'll see it anytime soon for lots and lots of reasons that we won't get into now. So N can be anywhere from 1 up to 7 because there are more or less those 7 rings or energy levels around an atom's nucleus in even the biggest of atoms. The larger the value of N, the greater the distance from the nucleus. In other words, when N equals 1, you're in the closest ring to the nucleus. Think about it like Mercury in our solar system. Earth being the third planet out would be an N equals 3, if you want to think about it that way. And lastly, the highest value of N that an atom has will tell you how many energy levels are in that element's atoms. So, for example, if we look at, say, sodium, sodium has N equals 1, 2, and 3 electrons within its atoms. And so that means that there are 3 energy levels in an atom of sodium because that's the biggest value for N that you'll find in sodium. And more on that later. You can think about the atom again kind of like this, where we have a nucleus, and this is kind of more like the Bohr model yet, but a nucleus surrounded by several rings, up to as many as 7 in the ground state of an atom. So when we see these 7 rings around it, for example, each of those represents an N value of 1 up to 7. Okay? And the text here you see on the right is the same that was on the previous slide, so you don't need to write it again. But it's showing it to us again in kind of a little bit more visual way. So if your N equals 5, if you're an electron and your N equals 5, I know right off the bat that you're somewhere in the 5th energy level, the one that's 5th out here from the nucleus. We have to go a little further then to talk about what kind of shape are you moving in, and which way are you spinning, and what's your orientation, those other quantum numbers. All right. The second quantum number is called the orbital quantum number. Sometimes you'll hear this referred to as the sub-level quantum number. So instead of the energy level, it's the sub-level. We won't use that word too often, but it will come up here and there. The orbital quantum number is abbreviated as lowercase l. And so this is a little lowercase l. I've used a cursive font here so that it looks like an L and not a 1. But it's a lowercase l. It doesn't have to be too fancy. The orbital, remember, is the region of probability where we expect to find an electron. The path in which we expect an electron will be found. They're very hard to pin down, electrons, and so all we can really do is make a pretty good estimate as to where we expect most likely to find them within the atom, because they don't act like normal particles or simple physical reality that we have with like finding a rock or your dog or your brother or something. Electrons move in a very complicated way compared to everyday stuff that we're familiar with, so their location is a little tricky. The orbital quantum number, again, tells us the shape of the electron's path within its energy level. That path can be rather simple or very complicated, but this quantum number will tell us what kind of shape the electron is moving in. Is it a spherical one? Is it a more complicated shape? And there are many different kinds. L can be any number starting from 0 up to n minus 1. Now that's a little weird looking at first, but let's say on the previous quantum number that n equals 3. That means the electron is in the 3rd energy level out in the atom, and that electron could have a value here of anything from 0 up to n minus 1, which would be 3 minus 1, right? So that's 2. So our second quantum number for that electron could be anywhere from 0 to 1 to 2. Now, later on, you'll see how this all comes together. So if that doesn't make a lot of sense to you yet, don't worry about it. It will when we start looking at the periodic table. But that's the range for L that you want to put into your notes anyway. For any known elements that exist today, there are no electrons that have any kind of L value greater than 3. Theoretically, they could, but they don't. We don't observe any electrons that have an L value or an orbital quantum number of greater than 3. So the only orbital quantum numbers that we're ever going to see will be 0, 1, 2, or 3. And trust me, that's going to be really good news because it keeps things a lot simpler for us. Now, if you go back to our ticket analogy, a lot of times when you buy a ticket for an event, you'll find that you have a section number and then you have a row. But the row is almost always given as a letter. Okay? It's just easier that way. If we use numbers and letters and numbers and kind of alternate, we can keep track a lot better. We see that even in games like Battleship, where you call J4. You don't call 10 4 because it's a little more complicated. So when we talk about sections, rows, and seats on your ticket, the rows are almost always in letters because it's just easier to go to row J, seat 7, and not have to worry about is that a J or a 10, and it's just simpler this way. And so we switch, in quantum numbers, we switch the second quantum number to a quantum letter, if you will. Now again, until we start working with these examples a little bit and doing what we call electron configurations in class, this might seem a little odd. But for now, I'd like you to just copy this table down and we'll work with it later together. On the very first column, you see here the possible values for our orbital quantum number, which we abbreviate as L. If L equals 0, 1, 2, or 3, we use instead, or we kind of substitute in, a letter. For L equals 0, we use S. For L equals 1, we use a P. For 2, we use a D. And for 3, we use an F. Now, S, P, D, and F might sound vaguely familiar from your 9th grade physical science class if you had a teacher who got into these a little more. It might not, and that's fine. But S, P, D, and F actually are abbreviations for words like sharp and diffuse. And what these are representing or telling us about is when scientists looked at those lines that you saw through the glasses and the funny tubes that we looked at. When you saw those lines, scientists were looking at very quality pictures of these lines, and they were able to describe those lines as being sharp or being rather diffuse or kind of fuzzy. And so they made really good observations of those lines, and they actually used those terms to describe the lines. And that connects back to quantum theory, turns out. More on that some other time. But for now, an S-shaped orbital has a sphere shape. So in the middle here you see spheres. A P-shaped orbital has what we call sort of a dumbbell or figure 8 or hourglass shape. A D-shaped orbital tends to have a cloverleaf shape, kind of a four-leaf clover most of the time. And you see here when it's an F sublevel, we say they have kind of a funky, crazy, complex shape. We're not going to try to put a name to them necessarily. So the only shapes that I want you to be concerned with are those S, P's, and D's. Spheres, dumbbells, figure 8s, and cloverleaf. And you'll see pictures of these as we go through and look at some examples of exactly how this looks within the atom. Finally, in the last column, orbitals come in sets. S orbitals come in a set of 1. It's a rather small set. P orbitals come in a set of 3, with 3 different orientations around the nucleus. D orbitals come in a set of 5, and F orbitals come in a set of 7. Hopefully you recognize there's a pattern there, 1, 3, 5, and 7. All right. Again, we're going to start looking at these as pictures and as what we call electron configurations and orbital diagrams, and this 1, 3, 5, and 7 will start making a lot more sense. Okay. I want to show you what those orbitals look like just real quickly so you can start putting a physical kind of picture to this. An S sublevel that has a sphere shape is exactly that. It's a round sphere like a ball that is centered on the middle of our nucleus. Okay, it's right on the center of the XYZ axis around the nucleus. A P sublevel has this dumbbell or figure 8 or hourglass shape, and you'll see there are 3 of them here. One is lying along the X-axis, one is lined up with the Y-axis, and one is lined up with the Z. Those are the 3 different positions that a P orbital can take. along the X, Y, and Z. And that's why there's a set of 3, because it can position itself along those 3. A D sublevel has 5 possible orientations, and you see those pictured here. Okay? You don't have to memorize these or be able to draw these, but this set of 5 different orbitals make up the D sublevel. And each of those 5 orbitals there, we'll find out, could have up to 2 electrons moving in that path. And finally, F has very complicated looking shapes. Looks like some sort of balloon animal. And these funny green 7 pictures here you see are the drawings that Schrodinger and his team eventually led us to, okay, that show us where we expect to find the electrons in these very complicated paths. Hardly any of these electrons are simply moving in a circle. Most of them are moving in a very complicated, multi-lobed, funky shape. And you'll find out more about that as we go. But those are pictures of those possible sublevel orbital shapes. That's where we're going to stop on this second video. We're not going to go any further than the first 2 quantum numbers for now. We'll come back together when I see you next and start working with those first 2 quantum numbers on the periodic table and then something called electron configurations, which are the first way of kind of organizing the electrons in a way that would kind of connect us to Schrodinger and the work that he did. We'll talk to you then.